Alright, my name is Wayne Lancaster. I'm doing my video project for bonding. And so I had to go over ionic bonding, covalent bonding, valence electrons, and periods across the periodic table and how they affect bondings. But I'm going to start off with a more general thing that's very important in bonding. It's going to be valence electrons. Now what valence electron is basically, if you remember back in an earlier chapter, we went over a little thing called electron configuration. For electron configuration, it is basically like each level had a certain amount of electrons to go in it, and you had to fill those up. So for example, hydrogen was 1s1. Helium is 1s2. Beryllium was 1s2, 2s1, and so on. Very important to bonding. And so what we remember about valence electrons is valence electrons are the ones that are left over, that are on the outside shell. They're the leftover ones that don't fit fully into those categories. So, for example, you can write this with a Lewis-Dot structure or a Bohr diagram, two different kinds. I'm going to show you both. For, not mistaken, oxygen. So, O right here, since it is in the group 16, because this is how you tell the valence, whatever group it is, that's how many it has left over, excluding 3 through 12. But O has 6 valence electrons. So what you're going to do, since there's an S2 level, you're going to fill that one first. You're going to go. There's the first one. And then now that you still have the P6 level, because you have to fill out 1 on each side of those first. That's how it works. You're going to go 1, 2, 3. Now that you've seen that, you have 5 total. There's 6. And next thing you're going to do is you're going to take one of them and add a dot to the other one. All right, and that's how you draw the Lewis-Dot diagram for it. For the Bohr diagram, it's very simple. Charge is a +6. On the first level, 2 dots. Second level, you have 2 there, so you're going to put, sorry, I can't tell them. 1, 2, 3. There you go. That's how you draw the Bohr diagram for oxygen. And that's how valence electrons work. It's basically they're the amount left over for each the leftover electrons that don't fit into a category. And this is going to be important for bonding because bonding revolves around these valence electrons. All right, next we're talking about ionic bonding, and ionic bonding revolves both around metals and nonmetals. So just so y'all don't get confused, black is going to be metals, blue, nonmetals. Okay, an ionic bond is when you have a metal bonding with a non-metal. Sorry, I'm just giving you, that's how this works. Now, on to the first important thing. They do not share their electrons. What usually ends up happening is you have one needs a certain amount left. So we're going to use oxygen again. No, sorry. Oxygen again. Okay, so there's a rule that goes along with this kind of bonding. And as we mentioned earlier, it has 6 valence electrons. Now, what's the important thing about the octet rule? Well, the way the octet rule works is basically because an 8 will fill out a shell, then the most you can have in a single thing, except for hydrogen, is 8. So, following the octet rule, when bonding a non-metal with a metal, is how ionic bonding works. So basically, we're going to get the metal. We're going to do magnesium because it has a +2 charge. meaning it has 2 valence electrons, plus oxygen, which has, as the aforementioned, 6. When you combine, not combine, these are not combined. When bonding, right, the way this is going to work is that these 2 are going to go to the oxygen to make it an octet. So, for example, this would now become, we're going to draw the exact same diagram of oxygen that we had. So we're going to use the electrons from the magnesium, that's why they're in black, to fill out this one. And now this oxygen is stable, which is how ionic bonding works. Also, ionic bonds do require electrovalence. That is the process of combining them. And that's how ionic bonding works, is it's between a metal and a non-metal. All right, so I just realized that the drawing at the bottom was out of the way, so I just moved it up so you can see it. But like I said, once you combine the 2, you have the drawing of oxygen that we have up there, and then you take the 2 magnesium to combine it into the oxygen, meaning the magnesium is now stable because it has no valence electrons, and the oxygen is stable because it also has no valence electrons. Therefore, is how ionic bonding works. But there's the diagram that I drew. All right, so next we're talking about covalent bonding. And the difference between covalent and ionic bonding is covalent is usually between 2 nonmetals, mostly. And the other thing about covalent bonding is that you're sharing the electrons, you're not taking away from one another. So let me give you an example. Oh, sorry, this is not the non-metal color. Oh my god. So ashamed. Oh, like we said, it has 6 valence electrons, because this is just an easy example to use. So back to our diagram from earlier. Plus the diatomic molecule of H2, or hydrogen, diatomic oxygen, which is just 1 di. Like we said, also the rule from earlier that I stated during the ionic bonding section is that the most hydrogen can have, it's separate from the octet rule, is 2 dots. That's the most dots it can have. So you can have 4 dots attached, no, 3 dots, it has to be 2 or 1 dots attached to a hydrogen. Now here's how this works. When you're doing covalent bonding, when you combine them at the end, like you do ionic bonding, well, it's not combining. I keep using the wrong word. When you bond, the difference is with this one, is you have your O diagram again. So every place you have 1, you add another 1. But when you write this one, you have the H, still has its 2. They're sharing their electrons. There's 2 H's in this one. Or there's H2. So each of the H went to 1 to make it stable. So now it is sharing those same electrons, making both of them stable. Difference between that and ionic bonding, the oxygen takes 2 away from the magnesium to make the magnesium stable, but they're not sharing them in a way. They're taking or giving away from another. Also, a thing I forgot to mention in the ionic section is that I'm running out of breath. All right, when you're in the ionic section, sorry I forgot to mention this. I'll mention this now. If you receive an electron like O does, you have a negative charge. And if you give away an electron like Mg does, you're going to get a positive charge. In the case this is +2, in the case of O, it is -2. Why did I write 6? Oh, no, I'm sorry. Yeah, -2. No, sorry, that's how much it loses. Its charge is just 6. Charge is 6, but whenever you're combining them, this is going to get 2 to make it 8. This donates 2. That is the reason this has positive, this has negatives. Let me just scoot it up for you. There you go. And that's how covalent bonding works. Last thing we have to talk about is periodic trends. As we know with the periodic table, there are trends that go across it. You know, this is going to be a really bad drawing of the periodic table. I'm so sorry in advance. So there's trends that go across this periodic table that make it different. So when it comes to reactivity, oh my gosh. Reactivity, how reactivity goes across this way, going towards the left side, it gets more reactive. And as you go up, it gets more no, I'm sorry. Bleh, I did it backwards for that part. When you're going down, it gets more reactive. Why is that? Well, it's a pretty simple explanation dealing with valence electrons. See, on the very right side over there that I just drew, those are the noble gases. They're the most stable elements because guess what? They have no valence electrons. They are completely stabled out. They have a full shell, meaning they don't really react with anything at all. Further you go this way, the less valence electrons, the less stable you are. So the further you go that way, the further you are from getting a full shell, meaning that they're more reactive on the left side. The reason it goes down has to do with the same trend of atomic radii, within the fact that the larger it is, the more reactive it is. So that's why when it's going down that way, this is what affects bonding. So the more reactive it goes across, the more bonding it does, which is why you don't bond with noble gases, because they're already full. They don't share their electrons in any way, which is how it works. This is the end of the presentation. I want to thank you. Again, my name is Wayne Langston. I hope I did good. Also, Ms. Cooper, I used the same setup I did last time, except it's a little more janky this time. Just thought I'd show you this. All right. See ya.